time and interest, both colleagues and fellow students. So today is a very important milestone in Fenglei's academic career. He has been with RPI and IBM couple of years, and he is a brilliant student and very good at mathematics. So we had multiple very inspiring discussions. Today we will hear his story, the whole dissertation research. So we will let Fenglei to present. Then students can ask questions. And later, and the faculty members will challenge Fenglei. And just the usual format. And look forward to Fenglei's presentation. Okay, go ahead, Fenglei.
Okay, so now let me share my screen. Can you see my screen?
Yeah, please use presenter mode.
Okay.
Yeah.
Okay, let's get started. Thank you everyone, and thanks for being here to support, and thanks for your time. I really appreciate that. So the title of this presentation is Innovating and Interpreting Neural Networks. So if someone asked me to use one sentence to summarize my research, so I would say in my PhD research, what I mainly did was to design new neural networks and develop their interpretation. But how to design new neural networks? We need to consider the elements of neural networks. The elements are including but not limited to aggregation function, nonlinear activation function, network architecture. So basically, aggregation function is how the input and the weights of neurons are interplayed. And after aggregation function, the nonlinear activation function is to get the output of the nodes given the result of aggregation function. Lastly, the network architecture. This one is the basic infrastructure of a neural network that defines the information flow. So the sum of my PhD research is to prototype advanced models by revising the above three aspects. And after getting new models, I will test the model's performance on some applications. However, I'm not just satisfied with getting new models with some good performance. I would like also to develop their interpretation such that the models I prototyped are not totally black box models. At least they will have some explanation. And this is the outline of my PhD research. Also the outline of this presentation. The first part is quadratic networks. In this part, we propose so-called quadratic networks, which is to revise the aggregation function. And in the second part, we propose a new kind of we propose a new kind of activation function. And in the third part, we propose an explainable topology, which is to revise the network structure. The fourth part is about the equivalency of width and depth, which is on the network structure as well. Lastly, we discuss some new topics and future directions. Let's first check the first part, quadratic networks. As we know, the invention of neural networks is to mimic the biological neural systems in the early history of artificial intelligence. However, we find one thing quite weird in current deep learning research, which is currently all mainstream deep learning models are based on one type of neurons, which cannot reflect the neuronal diversity of a biological neural system. as we know, in our biological neural system, there are many different types of neurons in terms of their morphology, biochemistry, properties, and so on. These different types of neurons working together to make the whole neural system function well. So we believe that diversity is the good thing. But currently the deep learning models do not have such kind of neuronal diversity. So our idea is to introduce the neuronal diversity for the deep learning systems. With this idea, we propose the so-called quadratic neuron by replacing the inner product with a quadratic function. Previously, a single conventional neuron cannot do the XOR logic because in a conventional neuron, the inner product is used. The decision boundary of the inner product is linear, so the linear decision boundary cannot classify the XOR pattern. In contrast, the decision boundary of the quadratic neuron is either parabolic or elliptical, so a single quadratic neuron can implement the XOR logic. Here, this is the quadratic function we use in the quadratic neuron. This quadratic function involves three terms, two inner product term multiplied together, plus a power term. So this is a specially designed quadratic function. Because here we have the power term such that the overall quadratic function can express a complete quadratic function, and also given the n-dimensional input, the number of parameters in our quadratic function is 3n, which is acceptable because it scales linearly with the number of input. Why we do this? It's because we consider that we will need to connect the quadratic neurons into deep networks. So we have to control the complexity of the neurons. If the complexity of the single neuron is too much, then the overall model will have unacceptable complexity. So this is why we do not adopt the general quadratic function, because given the n-dimensional input, the general function, the parameters of the generic quadratic function is n squared, which is too large. So since we have already got the powerful neurons, so what will we do next? So the answer is we will connect the powerful neurons into networks so that we can have even more powerful models. But before we do that, we need to derive the backpropagation algorithm for the quadratic models. Basically, the backpropagation algorithm for quadratic models has the similar principle with that of conventional models, because the core of backpropagation is applying the chain rule and calculating the derivatives. So the backpropagation algorithm for the quadratic models just using the different formulas to compute the derivative. And to evaluate the feasibility of the backpropagation algorithm for quadratic models, so we construct a network to classify the two spirals apart. Previously, some people reported that the standard backpropagation feed-forward network cannot classify such spirals without shortcuts. However, with quadratic networks, the standard backpropagation algorithm can classify these two spirals apart without the need of shortcuts. Here we explore theoretically about the model efficiency of quadratic models. Some people may have the concern about the model efficiency of quadratic networks because in the cellular level, the number of parameters of a quadratic neuron is 3 times of that of a conventional neuron. So people have the concern that if the quadratic model will have the model efficiency. So here we develop this theorem. So given the network with only one hidden layer, there exists a function that a quadratic network can approximate it with a polynomial number of neurons. But a conventional network can only do the same level approximation with an exponential number of neurons. So basically, in this theorem, we construct a function, and this function is very hard to be approximated by the conventional models, but it's very easy to be approximated by the quadratic models. So the function we constructed is a radial function, and the Fourier transform of a radial function will occupy the whole space. So if we look at the function of one hidden layer conventional network, when we do the Fourier transform for this function, you will find that the Fourier transform of the function of one hidden layer conventional network will support on finite lines, and each line is associated with neurons. Each line is associated with one neuron. So if we want to use one hidden layer network to represent a radial function, we need many lines to fill the Fourier space. But if we use the quadratic network to approximate a radial function, life will be much easier because radial function is a special case of a quadratic function. So the quadratic networks will be very suitable to approximate this radial function. So we do not need to assign a polynomial number of neurons for quadratic models. So this is why we have the exponential difference. So what can we get from this theorem? So we argue that the model complexity is equals to the structural complexity times cellular complexity. Although the cellular complexity of quadratic neurons is 3 times of that of conventional neuron, but for some tasks, the structural complexity of quadratic networks can be much reduced, such that the overall model complexity is also reduced. So this theorem tells us at least there will be some tasks or some functions that is very suitable for the quadratic networks. And here is the uniqueness about the quadratic networks. So I was often asked a question. So when you prototype a new neuron, so why not adopt? Why you adopt the quadratic terms instead of the cubic terms or even higher order terms? Here is the explanation. So basically according to the algebraic fundamental theorem, any polynomial can be factorized as the product of fourth order terms and the quadratic terms. So for the cubic terms or even higher order terms, they are just the combination of linear terms and quadratic terms. They are not as fundamental as the linear terms and quadratic terms. So this is the main reason why we prototype new neurons based on quadratic functions. And also, this uniqueness theorem opens a new door for the neural network to do approximation. And this is uniquely enjoyed by the quadratic networks because only with quadratic neuron, the network can do the approximation based on the factorization. And the previous theorems and preliminary examples show that quadratic models is a promising model. So so here we testify if the quadratic model can deliver good performance in solving some real-world applications. Here the problem we select is low-dose CT problem. This problem is a long-standing problem in CT reconstruction imaging because as we know, the X-ray dose will induce the risk of cancer. So patients always want to have as small dose as possible. But if we set the small dose for the imaging, then the resultant images will be noised. So the low dose CT problem is intrinsically a denoising problem. So here we prototype a quadratic autoencoder to learn a mapping between the noise CT images and the clean images. The experimental setup is as follows. The data set is a Mayo Clinical data set and some pre-processing steps. And we compare our model with CNN10, WGAN VGG, RED-CNN, and CPCE2D and BM3D. These models are all published in flagship journals, which can be considered as the state-of-the-art models. And also, as mentioned by Dr. Wang, and this model the paper that proposed this model was the second cited paper in the IEEE KMI journal. So this is a very good model. And the training protocol is mini batch training, batch size 50, 20 epochs, item optimization and mean square loss. And here is the result on the convergence behavior of different deep learning models. So based on this plot, we will have two observations. The first one is quadratic autoencoder achieves the lowest loss value. And the second observation is quadratic autoencoder descends faster compared to other deep learning models. This is the final denoising results. So I'm not the expert to read the CT images. So we rely on the doctor's opinion. So based on the doctor's opinion, we can conclude that the quadratic autoencoder image has lower image noise and maintain the conspicuity of vascular calcification, and quadratic outer images have a superior fidelity of small structures. In this slide, we compare the model efficiency of a quadratic autoencoder with other deep learning models as an evaluation for our theorem. So here, basically, we gradually increase the number of filters in each layer of models. As a result, the number of parameters for the models will also increase. And the key result is quadratic autoencoder can have a higher PSNR and SIM scores with less parameters. In the previous slides, we use PSNR and SIM to evaluate the image quality. This is good, however, it's not totally correct because SSIM and PSNR scores may not faithfully reflect the doctor's preference. An image with higher PSNR or SSIM score may not be the desirable images for the doctors. So here we prepare 20 de-identified cases that are obtained from different models, and then we invited 3 experienced radiologists to score them, and score them in terms of 3 aspects: image texture, noise, and fidelity. So based on the radiologist the study, we can say that the quadratic autoencoder overall has the best performance on the image texture and noise reduction and fidelity. Here we explore how to train a quadratic network. And arguably, currently there are three ways to train a quadratic network. The first one is random initialization. This is very straightforward. We just randomly initialize all parameters. However, in the experiment, we found that random initialization is not stable. We guess it is because the nonlinear magnification effect of a quadratic operation. So to address this problem, we propose the transfer learning strategy. So in this strategy, we first train a conventional network with the same structure of that with the same structure with quadratic network. And after the training, we get the parameters from the conventional network. Then we will use these parameters to initialize WR and BR. And for the rest parameters, we set WG as 0, BG as 1, and C as 0. Uh, uh, Overall speaking, transfer learning works well in the experiment, but transfer learning also has some drawback. For example, transfer learning introduces additional computational cost because we need to train an additional model. To address this problem, we propose so-called intro transfer learning by randomly initialize WR and BR instead of using the parameters from a conventional network to initialize. And for the rest parameters, we keep the same protocol with transfer learning. So why we set WG equal to 0, BG equal to 1, and C equal to 0? This is because if we set WG as 0, BG as 1, and this term will become identity. As a result, the quadratic model will degenerate into a conventional model in the initial stage. We think this is better because we do not want to specify quadratic functions for the quadratic model in the initial stage. We would like the quadratic models to learn the suitable quadratic functions itself in an adaptive way. Also, we can set different learning rates for WR, BR, and WG, BG, WBC. We argue that quadratic networks can have a guaranteed improvement. Let's imagine that we set learning rate of WG, BG, WBC as 0. Then these parameters will never be updated under the transfer learning and intro transfer learning. So it will mean that the quadratic model will always be the conventional model. So in this case, the quadratic model will at least have as good performance as the conventional model. But if we set a non-zero learning rate for WG, BG, WBC, these parameters will have some effect. And these parameters will be updated. And somehow these parameters can improve the performance. So to evaluate the intro transfer learning and the transfer learning, here we show the validation loss of the quadratic autoencoder trained by intro transfer learning and the transfer learning. And the key result is that the quadratic autoencoder trained with transfer learning and the intro transfer learning have the same level of validation loss. You can see that from this curve. So this is good news because 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 it means that the transfer learning is not necessary. We do not need to additionally train a conventional model to initialize the parameters of a quadratic model. We just use the intro transfer learning, which is good enough. And And here we further testify the effectiveness of intra-transfer learning. Here we conduct the image recognition task on the ImageNet dataset and validation and the safer-turn dataset. So here we replace the conventional neurons of ResNet with quadratic neurons, so that we get the quadratic ResNet. And basically, the quadratic ResNet have lower errors than the conventional ResNet. Here you can see that in the ImageNet validation set, the quadratic ResNet 34 can achieve the error of 24%, which is 1% lower than that of ResNet 34. Which can be considered as a big improvement. So the conclusion here is the quadratic networks trained with intra-transfer learning are better than the conventional networks of the same structure. We also develop an interpretation for the quadratic networks from the fuzzy logical point of view. So basically, we regard each quadratic neuron as a fuzzy logical gate. We classify the quadratic neurons based on their eigenvalue spectrum of the quadratic function in each quadratic neuron. So different eigenvalue spectrum means different fuzzy logical gates. As a result, a quadratic network is nothing but a deep fuzzy logic system. There are some follow-ups from GitHub. Some researchers are interested in quadratic models. However, we have to say that currently the quadratic models are not mainstream deep learning models. However, I'm a believer of quadratic models. In the future, I think we can try to find killer applications for the quadratic models, such that in a specific application, the quadratic models can be the top priority model. Then the whole story will be completed. That will be very great. Now let's move to the second part of this presentation. In this part, we borrow the wisdom from the wavelet shrinkage algorithm, and we propose a new type of activation function. And then we propose an explainable autoencoder. There is a growing interest in interpretability research. Here we plot the number of articles with respect to the year of publications about the topic neural network interpretability. You can clearly see the trend that the number of articles increased exponentially in the past years. Indeed, interpretability is a very hot topic because interpretability is a very important issue. No matter you are doing engineering research or the theoretical research, interpretability will be helpful. Together with my IBM mentor and my advisor, we wrote a survey for the interpretability of artificial neural networks. If you are interested in this topic, please check out this survey paper. As I mentioned earlier, we borrow the wisdom from the wavelet shrinkage algorithm. This algorithm is a very famous denoising algorithm in the wavelet signal processing field. So let's first check out the procedures of this algorithm. So given the authentic signal ST, and this signal was corrupted by the noise, and YT is the observed signal, which equals to the summation of ST and N. The first step of wavelet shrinkage algorithm is apply the wavelet transform for the observed signal to get the Y hat. Then we apply the soft thresholding on the Y hat with with a soft thread holding function. This function is look like this. So basically, any signal with the value smaller than the absolute value of B will be truncated. So after soft thread holding, we apply the inverse wavelet transform for the result of soft thread holding to get the recovered signal as hat. As you can see, the soft thread holding is the key element of wavelet shrinkage algorithm. But how it works? Let's see the right figure. The top left is the original signal, and the bottom left is the wavelet transform of this signal. You can see that the spectrum of wavelet transform is very clean. In contrast, the top right is the observed signal, which is signal plus noise, and the bottom right is the wavelet transform of signal plus noise. As you can see, they are full of glitches in the wavelet spectrum, and these glitches have a smaller amplitude. So if we apply the soft thread holding, we can remove these glitches such that the wavelet spectrum will be clean. So this is why the soft thread holding can help recover the signal by removing the noise. Inspired by the wavelet shrinkage algorithm, so here we propose a so-called soft autoencoder. In soft autoencoder, we utilize soft thread holding as the activation function in the encoding layer. While in the decoding layer, we utilize the linear function. So on the top level, in soft autoencoder, the convolution in the encoding layers can be understood as wavelet transform, and the convolution filter in the decoding layers can be understood as inverse wavelet transform. So as the whole system, the soft autoencoder is nothing but a deep cascade wavelet shrinkage system. So because we have established a mapping between the soft autoencoder and the wavelet shrinkage system, the soft autoencoder is not a totally black box. There is some interpretability for the soft autoencoder. Here we will compare the soft thread holding with other nonlinear activation functions, such as ReLU and its variants, leaky ReLU and concatenated ReLU. The idea of leaky ReLU and concatenated ReLU is that they argue ReLU will lose information because ReLU will ReLU will threshold the negative part of the input as 0. But there might be useful information in the negative part of the input. To address this problem, the leaky ReLU allows the decayed path for the negative part of the input. In contrast, the concatenated ReLU keeps both the positive part and the negative part of the input as two separate channels. So the dimensionality of the output after the concatenated ReLU will be doubled. So here we compare the denoising result of different autoencoders on the CIFAR10 dataset. The compared models are leaky AE. Leaky AE is autoencoder with leaky ReLU, and the ReLU AE and concatenated AE. As you can see, in a majority of cases, soft autoencoder has a superior performance compared to other autoencoders. Here Here we upgrade the soft thresholding into so-called generalized linear unit. We call it gen loop. As I mentioned earlier, the soft thresholding can do the denoising. However, if we allow the parameter b to be positive, it can promote the wavelet coefficients, which can have the effect of promoting resolution. So it can have some function of deep learning. So we propose a generalized linear unit called GenLoop to unify these two cases, B, to unify these two cases, positive B or negative B. So a single generalized linear unit can either do the denoising or do the deep learning, depends on the sign of B. And further, we argue that the network equipped with generalized linear units can simultaneously do the denoising and deep learning task. To evaluate this idea, we conduct the following experiment. The experiment setup is as follows. The data set is set 14, and we prepare low-resolution images by subsampling and upscaling. And we add Gaussian noise, and we prepare this number of high resolution and low resolution noise images. The backbone network is SR-CNN, super resolution CNN. This network is a first neural network model for super resolution. The result is shown in the right table. Again, in the majority of cases, Zhenlu SRCN can achieve higher PSNR and RMSE values. Here is the images obtained from different models. We can directly check the profiles. The red line is the profiles from the Zhenlu SRCN, and the black line is the ground truth label. As you can see, the profiles obtained from Zhenlu SRCN are closer to the ground truth label. Here we move into the third part of this presentation. In this part, we propose an explainable topology and address the question why shortcuts are powerful. If you have some experience in deep learning, you will find that currently the most popular network structure is the shortcut structure. Indeed, the network with shortcuts has shown to be very powerful in many important tasks, and usually the network with shortcuts is more useful than the network without shortcuts. However, we found that there are quite a few papers dedicated to explaining the power of shortcuts. However, we think this problem is an important problem because the shortcuts structure are everywhere. They are very important. So we think we need to explain why shortcuts are powerful. So here we propose a sparse shortcut topology and use this topology to explain why shortcuts are powerful. And this topology has been used in some papers before and shown some good performance. The basic characteristic about this topology is that all hidden neurons are wired with the output neuron. Here is the first result. Here we analyze the approximation ability of the proposed topology. The theoretical result here is that one neuron wide network with the proposed shortcut topology can approximate any univariate function. However, without the proposed shortcut topology, one neuron wide network cannot do the same job. So this result can justify the power of shortcuts because without the shortcuts, the one neuron wide network cannot do the universal approximation. And along this direction, here with the help of the shortcuts, we propose a wise-bounded universal approximator. Previously, the universal approximation theorem shows that one neuron-wide network with one hidden layer network with infinitely many neurons can do universal approximation. So in this theorem, the universal approximation is depth bounded, which has a finite depth but infinite width. And here the universal approximator is width bounded. The width is 2 times n squared plus n, given the n dimensional input. This width is a little bit larger, but it doesn't affect our conclusion. In addition to approximation ability analysis, we also conduct generalization bound analysis. So basically, the generalization bound can somehow characterize the generalization ability of a model. It's very likely that a model with a higher generalization bound will not scale well. So here we first calculate the generalization bound for the dense net, and then we show that the generalization bound of the proposed topology is tighter than that of dense net, which suggests that the proposed topology may generalize better than the dense net. This is the comparison between the proposed topology and the dense net to evaluate the generalization bound theory. So basically, from the table, we can see that the proposed topology can achieve lower errors with less parameters than the dense net on this dataset. We also evaluate the performance of the proposed topology on ImageNet classification task. The results are also good. You can see that the results of the proposed topology are comparable with other models. Here we provide unraveled views for ResNet topology and the proposed topology. You can see that in the proposed topology, the earlier layers are more important than the later layers because there are more passes going through the earlier layers than the later layers. So to evaluate this idea, we undo layer 1 and layer 5 respectively for the models obtained from a previous ImageNet experiment. And we found that undoing layer 5 will not affect the model performance too much. There is only 10% also drop. However, if we undo the layer 1, the performance drop is 40%. So this result somehow justify our idea that the earlier layers are more important than the later layers in the proposed topology. Now we come to the fourth part of this presentation. In this part, we discuss the relationship between the network width and the depth, and we find that the width and the depth of a neural network are equivalent to each other. The background is one of the key reasons that accounts for the successes of deep learning is the increased depth, because depth can allow a hierarchical representation of features. However, in the last 90s, wide networks are the mainstream models. There is the famous universal approximation theorem shows that wide networks have enough approximation ability. Also, in recent years, the term wide or broad learning was coined to complement deep learning. So the question is, width or depth, which one is more important? Furthermore, we ask, does neural networks have a directional preference? In this research, we provide an answer to the relationship between the width and the depth. Our result shows that the width and the depth are equivalent to each other, and they can be converted to each other. We justify our idea from two perspectives. The first perspective is De Morgan law. So a network corresponds to a root system. So given a network, after the network is trained, we can examine the parameters of this network and extract the roots from this network. For example, we construct a network to classify the iris dataset, and after that, we extract 3 roots from the network. In terms of the classification performance, these rules are as good as the original model. And in a rule system, a rule is of the format if input belongs to some interval, then the input belongs to some class. So functionally speaking, uh, uh, the rule can be approximately equivalent to the trapezoid function, as long as the delta is arbitrarily small. So in a rule system, we have the De Morgan's law, which is the intersection of roots equals to the negation of the intersection of negation of roots. Inspired by the De Morgan law, we can construct a deep network that can express the left side of the De Morgan law equation. And also we can construct a wide network to express the right side of the De Morgan law equation. Because the left side and the right side of the De Morgan law equation express the same thing. So the construct deep network and the wide network are equivalent to each other. So this example somehow suggests the equivalence between the width and the depth, which is good, but it's not totally convincing because this result is a constructive result. The only thing we can say from this construction is that the small set of deep networks and wide networks are equivalent to each other. To really show the equivalence, we need to generalize from this constructive result. So we develop our main theorem. So this theorem said that given an arbitrary ReLU network H, there exists a wide network H1 and a deep network H2. Both the wide network and the deep network can represent the original ReLU network. Can represent the original network arbitrarily well, and the error is measured by the area of inaccurate regions. This theorem is much more powerful than the previous construction example. As I mentioned earlier, previous constructive result just show that the small set of wide networks and deep networks are equivalent to each other. But here, with the help of our main theorem, we can say that the set of equivalent deep networks and wide networks are much bigger, big enough to claim equivalence. But how to prove the main theorem? Here is the sketch. So basically, we utilize the following two aspects. We utilize the following facts. The first fact is that a ReLU network partitions the space into many polytopes. Here, the polytope is the decision cell that is enclosed by the decision boundaries. Basically, a ReLU network is a piecewise linear function supporting over polytopes. And the second factor is a number of simplices constitute a polytope. So basically, in two-dimensional space, a simplex is a triangle. So a square can be split into two triangles. So according to these two facts, we can see that the function of arbitrary real network is actually a combination of linear functions over simplices. So to represent the function of arbitrary real network, the only thing we need to do is to express the linear function over a simplex. So we need to have a basic network building block to represent the linear function over a simplex. After we have such a building block, we can aggregate these building blocks vertically to get the wide network. And we can also aggregate these building blocks horizontally to get the deep network. As a result, the constructed wide networks and deep networks are can express the original real network. And also the constructed wide network and deep networks are equivalent to each other because they both express the same thing. Here is the second perspective, polynomial representation. So given a polynomial with 2n terms, we can have its continued fraction representation. In contrast, according to the algebraic fundamental theorem, we can have the factorization representation for the polynomial, because both representation can express the original polynomial. So these two representations are equal to each other. Furthermore, you can find that the continued fraction representation is of nested structure, which aligns with the deep network well. And the factorization representation is of product structure, which aligns with the wide network well. So inspired by this observation, we can construct a deep network which is suitable to represent the continued fraction. And we can also construct a wide network. This network is a quadratic network to represent the factorization representation, because continued fraction representation equals to the factorization representation. The constructed deep network and the wide network are equivalent. So this is another angle to justify the width and depth equivalence. As a summary, in this research, we elegantly derive width and depth equivalency from mathematical equivalency equations. The first equation is De Morgan law, and the second equation is polynomial representation. Now we move to the last part of this presentation. In the future, I would like to keep doing the graph embedding. This is the ongoing project with IBM. And also, I would like to find some killer applications for the quadratic networks. If I can find the killer applications for the quadratic models, then the whole stories will be complete. And lastly, I would like to see if there will be some applications for the equivalence idea. Here is a slide summarizing my publications and preprints. These are my first authored publications and preprints. This slide shows the co-authored publications and the preprints. I would like to thank everyone my advisor, my committee members, and my collaborators, and my lab members. I think without you guys' support, I cannot arrive where I am now. Thank you very much. I think that's all I have today. So any questions?
Okay, thank you very much, Fenglei. So now it's just the question and answer time. And the committee members hold your questions. And all fellow students, just audience, any questions, it's time to ask Fenglei. Any questions?
Hi, Fenglei. I have a question
Yeah.
regarding your first part of your presentation.
Sure.
Oh, I have a question about the initialization of your cultural network.
Okay.
So,
Okay, let me go to that slide. Okay.
Yeah.
This one?
I mean, oh yeah, this one, yes, this one. And I want to know the difference of these three different kinds of initialization method. Because I'm not sure I get your idea of the advantages of the intro transfer learning initialization. What's the difference between the intro transfer learning initialization and the random initialization? I mean the first one and the third one.
Okay, so basically in the random initialization, we randomly initialize all the parameters WR, WG, BR, BG, and WB, and C. But in the intro transfer learning, we only randomly initialize the WR and the BR. But for the rest parameters such as the WG, we set it to 0, and the BG we set it to 1, and the C set it to 0. And also also in the real experiment, we often set the WB as 0 as well. And
Okay, yeah.
And one thing I want to emphasize is that by setting different learning rates, I think the intro transfer learning can have a guaranteed improvement because if the learning rate of these parameters is 0, then in the setting of intro transfer learning, uh, uh, these parameters will never be updated, and the quadratic model will always be the conventional model. So which means the quadratic model will at least as good as the conventional model. And if we set the non-zero learning rate for these parameters will have some positive effect. Somehow they can make improvement.
Yeah, and what's the advantages when we use the intro transfer learning initialization method, but not the completely random initialization?
In my experiments, I found that the random initialization is not stable. Yeah.
Okay, so it comes from the stable reason, right?
Yeah.
About the space stability.
Yeah, because in my experiments, I found that in the later stage of the training, the loss will become oscillating.
Okay, thank you. I see that.
Very nice questions. So any further questions?
Hi, Fenglei. I have one question. It's about your quadratic layer. You mentioned that the quadratic layer can be equal to several linear layers. Have you computed the specific number that a conventional linear network requires to be have a equal performance with your quadratic network?
Oh, so you mean the compute theoretically or compute experimentally in some application?
For both.
Oh, I think it's okay. Okay, let me go to this slide. Okay, so it is true that the conventional network can approximate any function, right? Because this is due to the universal approximation theorem. But in terms of the complexity, it is up to the specific. It is up to the specified accuracy. It means which means how well you want the conventional networks to approximate the quadratic networks. So if you allow a large error, then the then the then the number of needed parameters will not high. But if you specify a lower error, then you may need many parameters. So this is my theoretical view about your question. And in and it is and the experimentally experimentally, if we compare the model efficiency of conventional models and quadratic models, I think it is depends on the task. So for some tasks, the quadratic models may have much lower parameters, but the conventional models may have a higher number of parameters.
Oh, okay. Thanks for your answer. And that answers my question. And I have another question. It's about duality or equivalence. When you mentioned the potential application, could you help explain that? What is the potential applications?
Mm-hmm. Uh, uh, I think currently this is a theoretical understanding for the neural network structures, and there is an idea in my mind, maybe the application of the equivalence idea. So in recent years, neural tangent kernel is a very hot topic. So the basic idea in the neural tangent kernel is that if a network has infinite wise, the network will becomes a kernel, which means the training of a network with infinite wise will degenerate into the kernel-ridge regression. So here we already developed the equivalence idea, right? So I'm thinking if we can also have the neural tangent kernel by increasing depth, so this is an interesting direction. I think is worth exploring. So in contrast to the neural tangent kernel by increasing width, maybe we can also derive the neural tangent kernel by increasing depth.
Okay, sounds exciting. Thank you.